Okay, kicking off momentum. It's topic number 4 out of the first part of the course, so we're pretty much a quarter of the way there, but what we have been doing is spending a little bit more time than you would think we normally would on some content that's actually pretty tough. So remember, the projectile stuff is going to come back in the electric fields, circular motion is going to come back in the magnetic fields. So we have been spending extra time, but it's very much deliberate practice. Okay, so kicking off, Newton's second law. Hopefully by now this wow, that's terrible. Hopefully by now, there we go, this is stuck in your brain. This is in fact a vector. So remember, forces are vectors, acceleration is a vector, because forces can act in a direction, you can accelerate in different directions. So in terms of Newton's second law as a vector, alright, I can write down a bunch of things like F equals ma. These are vectors, remember. I can also say that the acceleration of an object is defined as its change in velocity over some sort of period of time. So now what we're looking at is F equals m, and I'm going to replace all of that by all of this, delta V over t. So now what we're looking at is the force on an object is equal to its mass times by its change in velocity over time. So remember, in order to speed up or slow down, so change the velocity over time, you have to apply a force. Could be your right foot on the accelerator pedal, applying a force accelerating you forwards. Could be your right foot on the brake pedal, applying a force backwards, so slowing you down. Alright, in terms of particles colliding though, it's a little bit different. It's pretty much the exact same maths, the numbers just come from slightly different places. Alright, so I want you to imagine a ball. And this ball is moving at 10 meters per second because it hasn't been thrown very fast, and I'm going to make the ball a kilogram in mass just because it's going to make the maths a lot easier for me to do. And this ball is going to bounce off a wall, so that's a wall. It's a pretty good wall, you have to admit. Alright, so this is the initial state. So to start with, we've got a ball travelling to the right at 10 meters per second, and it's going to impact the wall. Now after it impacts the wall, it's bounced off. No, it's probably a different ball now. Look at the shape of that, that's terrible. Anyway, it's bounced off and it's still going at 10 meters per second, but it's going the other way. So I'm going to sort of, a little bit of dead air here, I want you to think in your head, what's its change in velocity? So it was doing 10 to the right, now it's doing 10 to the left. Has it sped up or slowed down? And how does that relate to its change in velocity? Alright, so a little bit of a hint, these things are vectors. So if we had VI, VF, change in velocity is V final, take V initial, or remember from the circular motion part where we had the big circle and it's coming off and the acceleration is towards the center, this is also the same as V final add, so plus the negative of the initial. So if this is VI, what are we doing? Same length line, opposite direction is negative VI. Okay, so now when we're doing VF plus the negative of VI, what we're really doing is just adding these two guys together. So what's our change now? Alright, so this is 10 to the left, this is 10 to the left. So our change is actually 20 meters per second, and remember this is a velocity, it's got a direction that way. Alright, so now when I come to work out the forces that are applied, the only other thing that I need is how long this impact took. So I'm trying to make something a little bit easy. I'm going to say that the time of impact was 0.2 seconds. It's actually really long for an impact, so that's 20 hundredths of a second, or when you click in a stopwatch is about that fast. Alright, so 0.2 of a second, really squishy ball, really heavy squishy ball that's squished or something. So what we're going to do now is work out the amount of force that was applied. So F equals ma is m delta v over t, and in this case here, mass of 1, the change in speed of 20, remember, 20 divided by 0.2. Crap, I want to do this to myself. And in this case, dividing by a fifth is the same as multiplying by 5, is 100 newtons. Wow, that actually came out okay. 100 newtons. This is a force. Force is a vector. It's got a direction. 100 newtons to the left. So this is the force on the ball. Newton has 3 laws. Third one says every action has an equal and opposite reaction. Where's the other 100? They can't just pop out of nowhere. So this other 100 newtons has to have done something. Alright, so that's something you guys can tell me when you walk in the door one day, where that other 100 newtons went. Okay. The last thing that I want to show you in this video, Newton's second law and momentum. So hopefully you've sort of tweaked maybe a little bit, and you've seen me do, you know, F equals ma is m delta v over t, F equals m delta v over t. So I'm going to write it a little bit more obviously, and we're going to look at that top line. P is mv. So remember last year, momentum is mass times velocity. We were doing the linear air track, so the cart's moving backwards and forwards, and you guys were using tracker for a little bit of it. I'll put the arrows back here to make some of you feel better. So what we've really got is, you know, m delta v, m delta v. We've actually got the same thing. I'm going to leave the delta because it's a change in momentum over time. So force is change in momentum over some sort of time period. Now I want you to think about back up here when we're accelerating or dabbing the brakes. The force is equal to a change in momentum over time. You apply a force, you change something's momentum. If you apply a force in the same way it's travelling, you will change the momentum, make it bigger. Apply a force in the opposite direction, you're going to change its momentum and make it smaller. Okay, so that's where this comes in. It's actually called impulse because it's a tiny little pulse of force that's actually applied. Alright, now there's another method that we can use to kind of look at this thing in terms of momentum and sum of momentum, change of momentum, and all of these types of things. And I think I might save that for the next video because it's going to take up a little bit of the page, a little bit of the screen here, and it's actually not tricky, but it may take you a couple of goes to follow it along, but once you're done, it'll click and you go, wow, that makes a fair bit of sense, and it'll clear up a lot of other issues. Alright, so wait for the next video, it'll be in there. Cheers.